Most RF signals are not periodic and do not repeat over time. Fourier series fails when signals are finite or continuously changing. The Fourier transform solves this by using a continuous frequency representation. Fourier series represents signals using discrete sinusoidal harmonics based on periodic repetition. A signal is assumed to repeat forever, and this repetition creates a structured set of frequency components. Each harmonic corresponds to an integer multiple of a base frequency, forming a clean and predictable spectral pattern in ideal mathematical systems. This structure works because periodic repetition forces energy to concentrate at specific frequencies. As a result, the frequency representation becomes discrete, meaning only specific lines exist in the spectrum. This makes Fourier series very effective for analyzing oscillators and ideal periodic waveforms in theoretical signal processing. However, real RF signals, such as data bursts, radar pulses, and noise, do not repeat indefinitely. Because of this, the assumption behind Fourier series breaks down, making it insufficient for analyzing real-world communication signals. The Fourier transform extends frequency analysis beyond periodic signals by removing the requirement of repetition. Instead of using discrete harmonics, it represents signals as a continuous integration over all possible frequencies. This allows any signal to be expressed in terms of frequency content regardless of its structure. In this framework, frequency is treated as a continuous variable rather than a set of fixed points. Every frequency contributes a small portion to the signal, and the Fourier transform describes exactly how these contributions are distributed across the spectrum. This makes the Fourier transform a universal tool in signal processing because it works for periodic signals, non-periodic signals, transient signals, and even random noise within RF systems. The time domain describes how a signal changes over time, showing instantaneous amplitude variations. This view is intuitive and directly linked to physical measurements such as voltage or current in circuits. However, it often hides the underlying frequency structure of the signal. The frequency domain represents the same signal in terms of its spectral content. Instead of tracking time behavior, it shows how much energy exists at each frequency. This reveals patterns that are not visible in the time domain and provides a clearer view of signal composition. In RF engineering, this distinction is critical because system behavior, such as filtering, modulation, and interference, is fundamentally determined by frequency content rather than time behavior. The Fourier transform produces a continuous frequency spectrum rather than discrete harmonic lines. This means that signal energy is distributed smoothly across a range of frequencies instead of being concentrated at specific points. This continuous distribution is necessary because real RF signals are not composed of isolated frequencies. Signals such as noise, pulses, and wideband transmissions naturally occupy a range of frequencies depending on their structure and information content. The continuous spectrum provides a complete mathematical description of how energy is distributed across frequency, which is essential for analyzing bandwidth, spectral efficiency, and system performance in RF engineering. The Fourier transform is one of the most fundamental tools in RF engineering and signal processing. It is used in spectrum analysis, filter design, modulation systems, and communication channel modeling. Almost every RF system relies on frequency domain analysis to function correctly. Spectrum analyzers directly visualize the Fourier transform of signals, allowing engineers to observe frequency distribution in real time. Filters operate based on frequency selection, enabling precise control over which parts of the spectrum are passed or removed. Modern communication systems such as Wi-Fi, LTE, 5G, radar, and satellite links are all built on Fourier transform principles. Without it, RF system design would lack a consistent mathematical foundation. The Fourier transform extends Fourier series by allowing non-periodic signals to be represented in a continuous frequency domain. It reveals the full spectral structure of real RF signals beyond periodic assumptions. This forms the foundation of modern signal processing and RF communication systems.